Okay. Hi. Sure if anyone's here yet. All right. So I'll do a few questions anyways, and then if there are any questions, I'll take any questions. So I'll be looking, I guess, at the 2022 midterm. So this is really kind of straight from the lecture from this year. So take a number n and returns a list of all the perfect squares between 0 and n. So I guess the only difference here is that we are supposed to return a list. So I'm now realizing that, hello. So I'm now realizing that this does have a bit of a complication in that we haven't quite gotten to the material that we needed to on Friday in order to do this. I'll quickly tell you what that is. It's really nothing. So this is about how you can build a list up in the same way that you built up strings in the lab last week. So if you have a list like this, you can say l.append, for example, 1, 2, 3, and then that would make it so that L is 1, 2, 3, 123. This session is about, so like what we said on Friday, right? So I'm just doing some questions from past midterms. So, okay. So with that, we're doing this question. So again, kind of in order to append an element to the list L, you can do dot append. So this is very similar. I guess the person left, so maybe expecting something else. So, so with that, we can do the question. So the question asks, get perfect squares, right? So we want all the perfect squares up to this, and we want them in a list. So here, really, all you need to do is exactly what we've done in lecture. So make one way at least. Make a function that checks whether a number is a perfect square or not. And then if it is a perfect square, then just add it to the list. That's one way. The other way is to keep going 0, 1, 2, 3 up until you exceed the number here. And then you'll stop building the list up. So let's do it that way. So I'll say k is 0. And I'll say while k squared is smaller or equal than n, then k squared is one of those numbers that you do want to have on your final list. So you'll append k squared to the list. And then once it becomes the case that k squared is not small equal than n, then you are overshooting, so that's not in the list anymore. So I'll just return result. So the way that would work is I'll say, for example, get perfect squares up to, let's say, 5. breakpoint here. And now, so initially res is just empty. And now we're saying k is 0, is k squared smaller than n? Yes, append. Is k squared smaller than n? Now k is, sorry, I forgot to say k plus equals 1, so that would be an infinite loop. So k is 0, so we appended 0 squared, so res 0. And now we say, okay, k is 1, append 1. K is 2, still smaller or equal than n. So append 2 squared. So result is now 0, 1, 4. Now k is 3. We're asking, is 3 squared smaller or equal than n? The answer is no, because n was 5. So we're done. And this res ends up being 0, 1, 4, which is what we wanted. So, okay. So let's do this one. So write the function that computes the product of the elements of a list of integer. So for example, we want for the product of 2, 3, and 4 to be, 2 times 3 times 4. So let's do that. So the technique here is to say, I want to multiply L0 times L1 times L2. And we'll compute it kind of the same way that we computed factorial. So we'll start with 1, and then we'll multiply 1 by L0, and multiply 1 by L1, and multiply 1 by L2. So we need to multiply it again and again by L0, L1, and 2. So here, I don't really need to know the location. I just need the first element, second element, third element, and so on. So I'll say for E and L, and I'll multiply result by. Okay. So here we're saying write the function with a signature duplicates, which returns true if list 0 contains at least 2 adjacent elements of the same value. I did it literally yesterday during the lab session because this is a question from last week's lab. So I'm not going to do it again. So here it's asking write code that repeatedly prompts the user for, scrolling here. So here I'm saying write code that, and that was for the record question 2. This is the question from last week's lab. So here we're saying write code that repeatedly prompts the user for input and then outputs the number of items that the user entered input before the user entered pumpkin spice latte without any capitalization. So we want to say 2 over here because it says pumpkin pie and then it says candy. And then this technically, right. So this would be like this. So here I actually fixed it to be without any capitalization. So it has to be like just precisely pumpkin spice latte. Okay. So count how many times has the user entered the order. Okay. Before pumpkin spice latte. So, all right. So what do we do here? What we want to do is we want to say, count how many times the loop runs that asks the user for input, and also stop the loop if the user has entered pumpkin spice latte. Right? So this is similar to an example in lecture. So I'll just enter it as PSL for pumpkin spice latte. And then the order, I will enter it initially as just nothing, and then num orders I'll enter as 0. And now I'll say, while order is not equal to stop loop order, get a new one. Order is equal to the input. What is your order? And I'll increment the number of orders by 1. So there's going to be at least one order because initially order is nothing and the stop loop order is PSL, so those are not equal. And then if I enter the loop, then I increase the number of orders, but if order has become PSL, then that would be the last order. Now, what we want is not the number of orders including PSL, but rather the number of orders not including PSL. So what we can do is we can say return num orders -1. Make sense? Okay. So here we have a matrix. So recall that the matrix, well, you would recall it if you saw next week's lab. So recall that the matrix can be stored as a list of lists. So for example, the matrix 0, 0, 0, 0, 1 can be stored like so. Actually, we have seen that in class last week as well as in some of the future labs. And what we want is we want to rent we want to actually return the sum of the matrices stored as a list of lists. Okay. So here again, unfortunately, I did not get to this part. And sorry. So I did not get to this kind of part here, which makes it so that the list becomes 1, 2, 3, 5. But other than that, this is doable, if not easy. So how do we do that? So let's recall how you would store the matrix in the first place. So this is one way to store a matrix. And then you might imagine saying, well, we'll have two matrices, right? So one like this, and then we'll have an M2 that's like this. Maybe it's a little bit different. And now what we want to do is we want to add up those two matrices. So we want to call matrix sum AB. So I'll do it in a way that's slightly bad, but doesn't use the append because maybe that's easier. So what I'll do is I'll make A be equal to A plus B. So how do I do that? Well, I need to add this guy here, and I need to add this guy here, I need to add this guy here, and add this guy here, and so on. So one way to think about it is I want to say A at I and J plus equals B at I and J for every possible I and J. What are the possible I and J's? Well, in our case, I goes from 0 to 1, and j goes from 0 to 2, right? Because here, there's 2 rows and 3 columns is one way to think about it. Another way to think about it is really M has 2 elements, so this list and this list. So you can only say M at 0 and M at 1, you cannot say M at 2. On the other hand, you could say M at 1 at 2, and this would be this guy. All right. Now, in general, this is kind of for those specific examples. So in general, what would it be? Well, it would be 0 and up to length of A minus 1, right? Because the first row is 0, and then the second row is length of this M minus 1. All right. So the j, on the other hand, would go from 0 and up to length of A at 0 minus 1. And why is that? Well, because this is the A at 0. So either one would work, right? So this is M at 0, this is M at 1. They're both the same length. They correspond to the number of columns. Okay. So we want to do this, and this goes like this. So how do we make the sum for every combination of i's and j's? Well, we just say, for I in range length of 8, and then for j in range length of A at 0. And length of 8, because length of the input matrix, is how many elements are there here. Each element is a row. And then length of A0 is how many elements are there in each of the rows, and this is the same as how many columns. And once we've added this 5 to this 5, 0 to 0, 0 to 0, and so on, A now contains the answer, so we can return A. So there is another thing that the question asks for, which is to return the string error if there is a dimension mismatch. So here I've just looked at the length of A and the length of A at 0. I have not checked that B also has, the correct i's and j's. So before I do anything, I can just check if length of A is not equal to length of B, or length of A at 0 is not equal to length B at 0, then I just return error right away. So that would be the solution. So question 5, we haven't done this material yet. This we actually have done, but this would be a more challenging question. This we haven't done. This we haven't done. And that's the end of this midterm. So let's maybe do kind of a few more. So here it says, write code to print all the even numbers between 100 and 200, including 200, one number per line. Okay. So this would be just for I in range 100 to 201, because you go up to 201, not including 201. Print I. This would be it. So last index, so return the largest index at which the element E appears in the list L. So unlike the first index, which is the example that we had from lecture, here, for example, we want to say this 5 appears at location 3, 0, 1, 2, 3. Okay. So one way to do it is to say, okay, initially current last index that I saw is -1, and then every time that I see E, I update current last index, right? So I say for I in range length of L, say if L at I is equal to E, then current last index is I. And then at the end, I just return the current last index. So the idea here is that I start initially by saying I have this list L. And I'm looking, for example, for the index of 6. I start at at -1, and then I say, is L at 0 equal to 6? No. Is L at 1 equals to 6? Okay. 1 is the location where I saw 6 last. Is this equal? No. Is this equal? Okay. Now 0, 1, 2, 3 is the location where I saw 6 last. I'll update current last index to 3. And then after I've looked through the entire list, I say, okay, I'll return current last index. All right. So here it actually says I should say none rather than -1. So instead of saying -1 here, I'll say none. Okay. We have not done this yet, and may not do it by the time the midterm happens. So smallest common multiple of 4 input integers. Okay, so the smallest common multiple is the smallest positive integer that is divisible by all of A and B and C and D. So this is kind of similar to the question from the lab about the least common denominator, but it's different in that, well, we're looking for a different quantity here. So the approach that we can take, though, the simplest possible one, is the same. We can just say, I'll try every possible answer, and I'll stop when I find the least common multiple. So how do I do it? So it's A, B, C, D. So what's the smallest possible least common multiple? Well, one kind of answer is 1. So why don't we, like, or 0, whatever, why don't we not like bother with it and just say, you know, the in range just to 0. And then the question is, where do we stop? So potentially kind of what could be the largest possible least common multiple? Well, it could be just the product of all of them, right? So A times B times C times D. Here the +1 is so that they also check A times B times C times D. And then it's definitely the case that this is a multiple of A and B and C and D. It could just be that the least common multiple is smaller than that, right? And that's because, for example, the least common multiple of something like 2 and 4 is just equal to 4. It's not 8, because 4 is a multiple of 4, and 2 is also a multiple, and 4 is also a multiple of 2. But the product would certainly do it. So I can just try every one of those, and then I can say, well, if this is divisible by A and by B and by C and by D, then I found my answer. If not, keep flipping. Do I need to say anything here? Well, not really, because it's definitely going to be the case that certainly A times B times C times D is going to be a possible answer. It's just possible that I'll return before that. I start looking from the smallest possible number so that if I return, I definitely returned the smallest possible one, because I keep going 0, 1, 2, 3, 4 until I find something that works. So that means that I'll find the smallest one.
Just a quick question. Will the Euclid algorithm could be used for this question?
I mean, so you could, in principle, kind of, so like so Euclid would be for greatest common divisor. So it's not kind of directly out.
Ah, okay, so this one's the case for least common multiple. So
Yeah, yeah. So like like you could definitely do a more efficient job of finding the least common multiple than just trying all the possibilities. It would probably be that you would just, like factor
yeah,
the numbers. Stuff like that.
and this is just the most straightforward way, I guess.
Yeah,
All right, thank you.
yeah. All right. So okay. So this example we have actually done. So this example is basically the same thing as the example from lecture with the passwords, but kind of with a bit of it with a bit of a twist, right? So what we're trying to do here is we're trying to have a particular sequence. So full costumes, costumes. And then if you have full and costumes and costumes, then you want to say are unlocked. Is it? Uh, should code with the argument. Right. So it should be full costumes, costumes, pumpkin, and then it's unlocked. Otherwise, it says locked. Right. So it's a little bit like project one. It's a little bit like a little bit like the kind of the example from lecture with the passwords. So here's kind of here's kind of one way to do it is we can just keep track. I'll do it the way it was done in project one. So we'll just keep track of what was the call before and the call before that and the call before that, right? So I'll say this, and I'll have the previous ones. And then I'll say if this is if this is the combination, right? Then we return unlock. So this is pumpkin, and then this is costumes, costumes full. In this case, we should say return unlock. And else we want to say return locked. And we also want to update previous and previous two and previous three. So like the easiest way to do it without kind of bothering too much, but this would involve kind of copying and pasting once, is to say, okay, so previous two, previous three is equal now to so previous is now input and previous two is now previous one. And previous three is previous two. And whether you're kind of locking or unlocking, you'll do it here as well. So, kind of a little bit ugly. So what you can do instead here is you can kind of first move and then do the thing, but then like you would have to do another thing. So like I think this is probably the easiest thing. So okay. That makes sense. So same logic as project one. Uh, the idea here, of course, is well that we need to say, you want to call it. And it'll just make them kind of nothing initially so that they don't unlock anything by accident. Okay. Haven't done this. Done. So the 2020 midterm was obviously kind of during the COVID year, so quite different. So let me just copy this. Okay. So here we're saying, write the function that returns the sum of the numbers 1 cubed plus 2 cubed and so on plus k cubed. So for example, some cubes should return 9, and that would be because it's equal to 1 cubed plus 2 cubed, so 1 plus 8, so that's 9. Okay. So this would be for I in range, 1 through k plus 1 because we want for it to include k. Okay. And we'll add I cubed to the results every time, and we'll return results over here. So this is like a little bit like the question about computing pi from the lab, where we're saying how many terms would it take in order for the sum to become greater or equal than n, right? Or we could do it directly in the way we did it for a question just, 15 minutes before. Let's do it directly, maybe. So what do we want to say? We want to say, let's keep going while the sum of the cubes is smaller or equal than n. And then once we go over, then we know that we're done. Okay. So I'll say current sum is equal to 0. And I'll say I is equal to 1. And I'll say while current sum is 0 actually. So I'll say while current sum is smaller or equal than n, I'll add I cubed to current sum, and I'll add 1 to I. Okay. And I'll keep going while it's the case that current sum is smaller or equal than n. So, for example, if n is equal to 1, what would happen? So if n is equal to 1, then the correct answer is 1. Yeah. So then the correct answer is 1. So what I would do is I would say, okay, initially, is current sum greater or small equal than n? Yes, it's 0. Okay, add 1 squared to current sum and add 1 to I. So then I'll say, okay, is now current sum small equal than n? The answer is still yes. So what's going to happen? Yes, I do want to start with 0. So what's going to happen is I is going to become 2. Once I has become 2, current sum is already larger. So then I stop. So so if I stopped, that means that current sum has overshot n. So I have one more term that I need. So I need to return I minus 1. Might be a little bit non-transparent. So let's trace it again. So let's say that n is equal to 1. So initially I is equal to 0, and current sum is equal to 0. So is current sum small or equal than n? Yes. Current sum plus equals 0. Okay. I plus equals 1. I is now 1. We now do current sum plus equals 1. Current sum is now 1. And I is now equal to 2. So now we're saying, is current sum greater, small, equal than n? The answer is it still is actually. So current sum is going to overshoot. So 3. And current sum is going to become 1 plus 2, 1 plus 2 to the third. So that would be 9. So now it's overshot. In fact, and I need to, in fact, return I minus 2. And that would be because I both overshot and I also counted 0 as a term. Does that make sense? So, yeah. So I minus 2 because I counts how many times I added, but here I added 0 cubed. And also I added an extra term, which made it so that current sum is actually greater than n. And I don't want either 0 or the last term, which actually made me overshoot. Okay. Okay, so a list contains 30 elements representing the rainfall during the months. So, for example, the following represents the rainfall data for Toronto in September. So what we want here is a list that contains the 3-day moving average precipitation for days 2 to n minus 1. We technically, again, haven't done this because we haven't done append, but I've now told you about append, so that should be straightforward. So I'll make moving average be initially nothing, and then I'll say I want to start from index 1, and I want to add at index length of L minus 1. And I want first the average of those guys, and then the average of those guys, and then the average of those guys, and so on. So I'll say for I in range, so starting from 1 and up to length of L minus, so up to, so I don't want to go up to this guy, I want to go up to this guy. So it's the second to last, so that's why I say up to length of L minus 1, not including length of L minus 1. So this is at length of L minus 2. And I'll add the average here. So this would be, one way to write it is using the built-in sum function. So why don't I do that? Or maybe keep it simple. So L at I minus 1 plus L at I plus L at I plus 1. All divided by 3. And then we return result. So this one we still technically haven't done, so maybe I'll leave it for tomorrow and I'll teach you the thing that you need for it, and then we'll do it tomorrow. Uh, and then this one, again, let's do it tomorrow, just so that there's something to do tomorrow. Okay, so I'll do, I guess, the last two questions from 2020 tomorrow. Okay, question.
Excuse me, I have a quick question.
Mhm.
Is the Hopfield Hopfield energy network energy gonna be also on the midterm?
I mean, it was on the quiz, so like in the same way, you know.
Hmm.
So,
So
I mean, like I can't include everything on the midterm that we
ah,
did in lecture, right? But it
okay.
was, you know,
All right. Thank you.
yeah.
So are we actually gonna go over a Hopfield network energy review tomorrow?
If people ask, sure, yeah,
Oh, thank you.
yeah. Okay. All right. See ya.
All right. Thank you.